Hello everyone, welcome back to the channel. Today we're going to look at 3D mixed heat transfer, looking at both natural and forced convection with the addition of radiation cooling for electronic components. The problem we're going to look at today comes from Fundamentals of Heat and Mass Transfer textbook by Bergman and Levine, if you want to follow along. The problem reads as follows. Chips of width L equal to 15 millimeters on a side are mounted to the substrate that is installed in an enclosure whose walls and air are maintained at a temperature of T surface and T ambient of 25 degrees Celsius. The chips have an emissivity of 0.6 and a max allowable temperature of 85 degrees Celsius. We have two problems that we want to solve today. The first problem, problem A, reads, if heat is rejected from the chips by radiation and natural convection, what is the maximum operating power of each chip? The convection coefficient depends on the chip-to-air temperature difference and may be approximated as H, which is the heat transfer coefficient, is equal to C times the change in temperature to the 1/4 power. And we are given C, which is a value of 4.2 watts per meter squared K to the 5/4 power. The second question that we want to solve, we're going to add forced convection, and it reads, if a fan is used to maintain airflow through the enclosure and heat transfers by forced convection, with a heat transfer coefficient of 250 watts per meter squared Kelvin, what is the maximum operating power? We're going to start by decomposing the problem into our knowns, our unknowns that we want to find, and make some assumptions to solve the problem. So the knowns that are given to us, we know that the temperature of the enclosure as well as the ambient temperature is 25 degrees Celsius. We also know that the chips can sustain a maximum temperature of 85 degrees Celsius and have an emissivity of 0.6. By calculating the total area of the top of the chip, we know that we have an area of about 9.4 e to the negative 4 meters squared. Our heat transfer coefficient for natural convection is given to us in an equation with a constant, which is provided. And for forced convection, we're given a heat transfer coefficient of 250 watts per meter squared Kelvin. What we want to find for problem A is we want to know the maximum power dissipated by each chip with natural convection and radiation, and that is going to be in units of watts. For problem B, we're going to add forced convection, and again, want to know the maximum power that we can dissipate from each chip with the forced convection and radiation. So we're going to start by solving these by hand, and then we'll use those values to compare to the CFD simulation. So looking at our schematic, we have these 4 chips which are 15 by 15 millimeters and spaced roughly 30 millimeters apart in both directions. The chips are attached to a substrate, and we're told that both the backside of the chips as well as the sides of the chips are all adiabatic, so there's no heat transfer around any of those surfaces. So our only heat transfer is going to be from the top of the chip. We also know that our chips are located inside an enclosure, and we're given both the temperature of that enclosure as well as the ambient air temperature inside that enclosure. Some of the assumptions that we're going to make to simplify the calculation is we're going to assume that it's steady state. We're going to assume constant thermal properties of both the chips and the air. And we're going to assume that the chips are relatively small when compared to the enclosure, which will help us simplify the calculation of radiation. So we'll start by solving these problems one at a time. Starting with problem A, we can start with the given heat transfer coefficient that was provided. So we have this equation, H, which is the heat transfer coefficient, is equal to C delta T to the 1/4 power, and we're given the value of C, which is 4.2. We can plug in that C value as well as our temperature values in Kelvin, and we can see that we have a heat transfer coefficient of approximately 12.524 watts per meter squared Kelvin. We can then use that heat transfer coefficient and Newton's law of cooling, which is defined as HA delta T, to calculate the heat loss due to convection. So we'll plug in 12.524 for the heat transfer coefficient, our calculated area, as well as our temperature difference, and that will give us a rough heat loss due to convection of about 0.7063 watts. For radiation, we're going to use this simple equation of E, which is the emissivity, A, sigma, which is the Stefan-Boltzmann constant, and then the difference in temperature to the 4th power. Plugging in 0.6 for the emissivity, which we are provided, as well as our area, Stefan-Boltzmann constant, and the difference in temperature to the 4th power, we can see that our heat loss due to radiation should be about 0.2731 watts. We can then simply add the heat loss from convection to the heat loss from radiation, and determine that in this first part, or problem A, we should expect about 0.97945 watts dissipated from all 4 chips during this initial problem, with just natural convection and radiation from the chips. For problem B, we're going to assume that the radiation is not going to change since the radiation is not dependent on any of the airflow conditions. So we're just going to assume that the radiation is still 0.2731 watts. We can also assume that because our chip temperature as well as our ambient temperatures are not going to be changing. We'll then take our new heat transfer coefficient, which is 250 watts per meter squared Kelvin, which was provided, and we can again plug that into Newton's law of cooling. And we can calculate our forced convection number, which is going to be much higher than the natural one at about 14.1 watts. Again, adding the forced convection plus the radiation, we should expect in this second test case that we get about 14.3731 watts of dissipation from all 4 chips. So now that we have the analytical equation solved, we can set up a CFD model and see how close of an agreement we can get between our hand calculations and our simulated model. Our simulated model is going to look like this. We're going to have the 4 chips located on the back side of the enclosure as stated in the problem. Our enclosure is going to have a pressure outlet in the bottom, which is going to be stated as P equals 0, and a pressure outlet at the top of P equals 0 as well. The temperature of the air coming in is going to be 25 degrees Celsius, and the temperature of the chips is going to be set to 85 degrees Celsius. All the enclosure walls are going to be assumed to be adiabatic as well as the backside of the chips, which means that we're going to have no heat transfer outside the walls of the enclosure. So when we're doing the simulation, the first thing we have to determine is what viscous model should we use. And to do that, we can actually look at the Grashof number. And the Grashof number will show us the ratio between the buoyancy forces due to the variable density of the air versus the viscous forces in that air. This is analogous to the Reynolds number in a forced convection case. And in this case, our calculated Grashof number is about 2.85 e to the 4th. And if we look at these simple empirically derived brackets, we know that between 10 to the 3rd and 10 to the 6th, we can assume that the airflow is going to be laminar. Therefore, our viscous model for this first case with natural convection, we're going to use the laminar model. The radiation model that we're going to use is one of the simpler radiation models and works very well when we have gray diffuse bodies and we're not transmitting any radiation through opaque solids. And that model is called the surface-to-surface model. And we're going to skip over derivation of a lot of the math, but really what's going on here is we're going to calculate this radiosity vector, which is going to be essentially the energy transferred from one surface to another. And to do that, we first calculate this F value, and this F value is referred to as the view factor. The view factor is calculated before we actually calculate the simulation, so we'll go through, we'll look at the entire domain, and the view factors will be calculated and then stored in the matrices to be used in further calculations. And up here we can see a rough diagram of roughly how the view factor is calculated. It will look at one surface which is emitting energy and one surface which is receiving energy and calculate the view that those two surfaces have to each other and then use that in the calculation of radiation. So without further ado, let's hop over into Workbench and we'll get this model set up. So now that we're in Workbench, we're going to start by coming over to our analysis systems here, and we're going to drag over a fluid flow window, and we'll right click on the geometry tab and start a new space claim geometry. So in space claim now, we're going to start by sketching out the chips, and we're going to do that by going to sketch mode and creating 4 rectangles, and these rectangles are going to be 15 by 15 millimeters. And we'll go ahead and come up here to the sketch tab and use the dimension tool, and we'll add some dimensions to each of our rectangles to make sure that they are maintaining the dimensions that we want. And then we're going to add dimensions for the rectangles between the rectangles themselves and the center axis to make sure they're spaced out 30 millimeters apart from each other. So now that we have all of our chips sketched out and dimensioned, we'll go ahead and come up to the Design tab. We'll click on the Pull tool. We'll select each surface that was just created from our sketch. And we'll go ahead and just type 6 on the keyboard, and we're going to make these 6 millimeters tall. Go ahead and click enter. So now we have the solid bodies for each of our 4 chips. The next thing we need to do is create the enclosure. So to do this, we'll come up to the design tab. We'll go to sketch mode again, and we're going to place our sketch at the Cartesian coordinate system to make sure our sketch is located at 0, 0. We can use the view factor coordinates in the bottom here to change our view to look directly down at our plane. And we'll go ahead and sketch a rectangle for our enclosure. So our enclosure is going to be 150 millimeters in width by 300 millimeters tall. And again, we can add dimensions to that to make sure that we retain those dimensions. And then we're going to dimension off the axes of our sketch. And we're going to place the chips a little closer to the bottom of the domain or the inlet of the domain. So we're going to have 100 millimeters from the bottom edge to the central axis. And then we'll just center the chips relative to the y-axis. So now that that's done, that's our first 2 dimensions of our enclosure. And we're going to pull again. But before we pull, we're going to want to make sure that we turn off our solid domains here, or our solid chips, to make sure they're not combined into our enclosure. So we can now go back to the design tab, select the pull tool, and we're going to pull this enclosure out 100 millimeters. And once that's done, we can turn back on our chips and we can flip around and take a look. And now to make it a little bit clearer to see, we can go ahead and select all the bodies in the domain. We'll right click and we'll come up to the colors tab, and we can go ahead and randomize the colors to make it a little bit easier to look at. The other thing we can do for our enclosure is we can click on it and change it to transparent, since it's going to be our fluid domain. We need to remove the volumes of these chips from our air enclosure. And to do that, we'll again come to the design tab. We can use the combine tool. We'll select the air enclosure, and then we'll select each chip and delete the volume that was created. So once that's done, if we select all these chips and we hide them, we can see that we remove their volumes from our air enclosure. So the final thing before we move over into Fluent is we're going to want to turn those chips back on. We'll come up to the Workbench tab, and we'll go ahead and share the topology. When we share topology, what that allows us to do is it tells Fluent that each of these walls between the fluid and the solid are going to be in contact. And when we mesh it, we're going to want a conformal mesh at that point. So we're going to share that geometry. When we see the colored lines, we know that each was shared correctly. We can go ahead and move over into meshing and get our mesh worked out. So now that we're in meshing, the first thing I'm going to do is make our enclosure transparent again, just to make it a little bit easier to see what's going on. So we'll come up to the geometry tab. We'll find our fluid domain. In the details window down here, we can expand the graphics properties and change the transparency to make it a little bit more opaque. And now that that's done, the first thing I always like to do whenever I'm in meshing is to do my name selections. So we'll start by selecting the body tool up here, and we'll name the bodies. So we'll start with our air domain. We're going to go ahead and click N on the keyboard, and we're going to call this fluid. For the chips, since they're all going to be assigned with the same values, we're going to go ahead and select all the chips together. Again, click N on the keyboard. And we're going to call these chips underscore solid. When we add the solid or the fluid in the name of the name selection, it lets Fluent know what these bodies are going to be, and it will automatically set the cell zones, which will save us a little bit of time in our Fluent setup. So the next thing we want to do is define our faces. So we'll come up, select the face tool here. And same thing with our inlet and outlet. We're going to name these as the type of inlet or outlet that we want. So we're going to call the bottom one a pressure inlet. Same thing for the top. We'll call it a pressure outlet. And then we'll go ahead and select all of the faces of the enclosure. And we can call those enclosure walls. Again, denoting it as walls will allow Fluent to know that these are all going to be wall faces as well, and it will set them automatically. So we can go ahead and right click and hide our enclosure and take a look at our chips here. So as we know from our problem setup, the back faces as well as the side faces of all the chips are going to be adiabatic. So we're going to define those as a single set of walls. So we'll select all of those faces of the chip, including the back face, and we're going to name those chip walls. The front faces of our chip are where all of our heat flux is going to be coming out of our chips and into our air domain. So we're going to name those separately. So we're going to select all those faces, hit N on the keyboard again, and we're going to call those the fluid face or fluid walls. Now that we have all of our name selections, we can take a look at them over in the window here and make sure they're all set. And we're going to go ahead and start meshing. So we're going to start in order of where we want kind of the most refinement and then work out to the enclosure. So we're going to start by selecting these chip bodies. We'll click on the meshing tool to make sure we're in the meshing workflow. And we can right click and insert, and we're going to insert a sizing to add a body sizing to each of these. So for these chips, we know that we want a size of about 1 millimeter, so we get good resolution. And with that body sizing set, we can go ahead and select all the bodies again, right click, and generate the mesh on these selected bodies. And if we click on the mesh tool, we can take a look at what our mesh looks like. So you can see each chip is meshed with a structured mesh with about 6 elements going up in the Z direction, which is good enough resolution for this problem. So the next thing we want to do is we'll go ahead and right click and invert visibility to take a look at our enclosure. And since we have wall bounded flows, or all the walls of the enclosure, as well as the walls of where the chips are, we're going to want to add some inflation layer to make sure that we capture both the velocity boundary layer as well as the thermal boundary layer. So we'll go ahead and select the body tool. We'll select our air enclosure and we'll right click and insert an inflation. And now that the body is selected, it's asking for the boundary, which is going to be the faces that we want inflation on. And that's going to be all of our wall faces. So that's going to be all of the walls of the enclosure, as well as all the walls of the chips. So we'll go ahead and select those all as well. And we can go ahead and click apply in the detail window down here. And we're going to go ahead and use smooth transition with a maximum layer of 5 inflation layers on all the faces that we defined. So finally, before we mesh the enclosure, we're going to want to make a few changes to the global settings of our mesh. So if we select the mesh tab, we can come down to the details window here. We're going to start by changing the element size, which is going to be the maximum mesh size on our grid. And we're going to make that 6 millimeters. We're also going to expand this sizing tab down here, and we're going to change the growth rate as well. So the growth rate determines how fast we're going to go from small elements and increase those elements into larger elements. The default value is 1.2, or about 20% change for any neighboring elements. I like to make that a little bit lower because we want to make sure that our transition from our small elements to our big elements is pretty gradual, which can improve the reliability in the solving of our numerical solver. So I'm going to change that to 1.05, or a 5% change. And with that done, we can go ahead and generate the mesh. So we'll click generate mesh. And this will generate both the mesh of the enclosure and the chips. So with that done, we can take a look. As we can see, our chips are going to be the smallest mesh elements because we set those to 1. And we're going to get a gradual increase in the size of the mesh elements as we go from our chips out into kind of our free stream of the enclosure. And if we also take a look here at the top of our domain, we can see that our inflation layers, or those 5 layers of small cells on all the walls, were made correctly. So the last step we want to do here is go ahead and click the update button, and that will transfer our mesh into Fluent. So we can see that the mesh translation to Fluent was successful, and we can go ahead and close out of the meshing window and open Fluent and set up our model. So now that we're back in Workbench, we're going to go ahead and double click on the setup window. We're going to want to turn on double precision to improve the round off error of our simulation. And we can increase the solver processes to 4. The student license is going to limit you to using 4 cores of your CPU, but if you're on a non-student license, you can increase this number up to the number of cores that your computer has. And we'll go ahead and click Start to start the Fluent launcher. So now that we're in Fluent, the first thing we always want to do is come up to our domain tab here, and we'll do a quick mesh check to make sure we don't have any errors. And if it says done down here, it means that our mesh is okay. You can also go ahead and check the quality of our mesh by going to quality and evaluate mesh quality. And we can see that our minimum orthogonal quality is about 0.16 and our maximum aspect ratio is about 30. And the aspect ratio is going to be a little bit high because we added those inflation layers, but we know that those are going to be okay. If we had any serious mesh quality issues, you will get an error message here, and you can use some of Fluent's inbuilt tools to help you fix some of those mesh problems, or you can go back to the meshing tab and try to improve your mesh quality before coming into Fluent. So as always with our setup, we're going to start working down this left side here in order. So we'll start in the general tab, and we know that we're going to do a steady state simulation, so we'll leave our time on steady. Since we're going to have buoyancy driven flow, we're going to want to turn on gravity. And we can also come over to the right side of the screen here and turn on our axes or our show axes tool to make sure that we're setting gravity in the right direction. So in this case, our Y direction is our vertical direction or up direction. Therefore, our gravity is going to be set as a negative 9.81 meter per second squared in the Y direction. We can move on to the models tab here. And we already know, based off the Grashof number, that we're just going to have a laminar simulation. So we'll change our viscous model to laminar. We'll also turn on energy since we're doing a thermal modeling or heat transfer model. And we're going to go ahead and turn on radiation as well. So we can go ahead and select our model. We'll select the surface to surface model, and this will open up the radiation model window. So the radiation model, specifically the surface to surface model, as your model is iterating through and calculating the flow field, it's going to solve the radiation model a certain interval during each flow update. In this case, the default value is 10. So every 10 fluid time steps, it will go ahead and calculate the radiation and add it to your energy equation. And we're going to leave that on default. We can leave the maximum number of radiation iterations to 5 as well as the residual criteria for the iterations at 0.001. The last thing we're going to want to do is we can go ahead and compute/write our view factors, and this is going to be done before we start calculating. So we'll click on write. It will automatically open up to your workbench file. We'll click OK. And you can see now it's going to calculate our view factors and create surface clusters for our radiation calculation as we start calculating the model. So now that our models are set up, we'll start moving through into our materials. And so for our materials here, we're going to have our air. And since we do have buoyancy driven flow, we do want to model the change in density as it changes temperature. So we'll change the density from constant to incompressible ideal gas. Since our pressure is low and our temperature differential is pretty low, incompressible ideal gas should give us a pretty good assumption of how the temperature or how the density is changing with temperature. Go ahead and change and create. And for our solid materials, by default, it's going to be set to aluminum. And we're going to use aluminum for our chips. And we'll keep all the material properties constant and at the default values. And with our material sets, we'll go ahead and keep moving onto our cell zone conditions. So the first thing we're going to want to do, we can see that Fluent automatically assigned a fluid to our fluid domain or our enclosure, as well as a solid to our chips domain. If these weren't set correctly, we can always right click on them, come down to type, and switch between fluid and solid if your domains were not read in correctly. And by default, it's going to apply air to your fluid domain as well as aluminum to your solid domain. So we're just going to check the fluid domain, make sure it's set to air. It looks good, and we can apply that. For our solid domain, we're going to confirm that aluminum is being defined. And then we also know that each of our chips are going to be at 85 degrees Celsius. So we're going to set that as a cell zone condition here. So we can select the fixed values. We'll come over to the fixed value tab. As you can see, we now have an option for temperature. We'll go ahead and create a constant temperature. And we'll define this as 358 degrees Kelvin, which is equal to 85 degrees Celsius. And we'll go ahead and apply that. So we'll keep moving down the list here. We'll look at our boundary conditions. So we can look at our inlet condition. We can see that it was correctly assigned as a pressure inlet. We're going to leave our pressure as 0 for natural convection. We can come over to the thermal tab and set our inlet temperature, which we know is going to be 25 degrees Celsius or 298 degrees Kelvin. We also now have this radiation tab since we turned on the radiation model. So in this radiation tab, we can set what the external temperature is going to be, and that can either be the boundary temperature or we can change it to a specified external temperature. In this case, since our inlet is going to be at 25 degrees C already, we'll leave it at boundary temperature. The other thing we can change here is the emissivity. So if the emissivity of either the walls or the inlet or whatever we're assigning here is not a perfect black body or an emissivity of 1, we could also change that value. But in this case, we're just going to leave it as 1 for these surfaces. So we'll go ahead and click apply for that. Next, we're going to go to our pressure outlet here. Again, we're going to confirm that we have 0 pressure on the outlet. We'll come to our thermal tab and set the backflow temperature. So if there's any recirculation in the outlet, to our 25 degree ambient temperature. And again, just check that the radiation is set to 1 and boundary temperature. And go ahead and click apply on that. So the last thing we want to do is we want to look at our wall faces here. So we can see something that is going on here. So for some of our walls, we have both the wall and then a wall shadow. So these are all our coupled walls. And what happens is when we have a solid wall in contact with a fluid domain and we use shared topology, Fluent is going to read that as a coupled wall and create a wall and a shadow pair. So we'll have one wall in the solid, one wall in the fluid, and it will create a coupled connection between both of those. So our first wall that we're going to look at, which is going to be our chip walls, which we know are going to be all of our adiabatic walls, and in connection with the fluid, we want to make sure that there's no energy being transferred out of those walls. So we're going to come to the thermal tab. We're going to change this from coupled to heat flux and set heat flux to 0 to make these all adiabatic walls. Also in the radiation tab, we also don't want any radiation out of these walls. So we're going to uncheck this checkbox so it will not be included in the view factor calculation, and we'll set the internal emissivity into 0. And when we make that change, we will have to recalculate our view factors since we are removing some faces from our view factor calculation. So as we click apply, we will get this error message telling us that we must recompute our view factors, and we'll go ahead and do that before we start the calculation. And we can take a look here at our fluid wall and the fluid wall shadow, which is going to be the top face of all of our chips where all of our thermal energy is going to be transferred. And we just want to check and make sure that that thermal condition is going to be set to coupled. As well as with the radiation here, we know given from the problem that our radiation or our emissivity is going to be 0.60. So we can set that emissivity value here and go ahead and click apply. Before we move on, we'll actually go back to our models tab and we're going to go ahead and recompute the view factor since we made that one change. And to do that, we just have to open up the radiation window again, click on compute right. We'll select the file we already wrote to, and it will ask us if we want to overwrite, and we'll say OK. And this is going to go through and recalculate our view factors without those faces that we did not want to include in our radiation calculation. Go ahead and click OK. So moving on from boundary conditions, we can skip over a lot of these for the time being, and we can go down to the methods tab. And we're going to leave our pressure velocity scheme uncoupled. The other big change that we want to make here is for our pressure discretization. So whenever we're doing buoyancy driven flow, we want to make sure we're using either Presto or body force weighted. Using second order or some of these other pressure discretization schemes is going to give us some inaccuracies in the calculation of our buoyancy force and our natural convection. So in this case, we're going to use Presto. For momentum and energy, we can leave those on both second order upwind. We're going to leave the pseudo time step method, which can help a lot in natural convection simulations. And we're also going to turn on this high order term relaxation, which can help smooth out some of our numerics. Coming to the controls tab, we can leave all of our under relaxation factors as the default values. And the last thing we're going to want to do before we start solving is create a new report definition. So whenever you're solving a CFD model, you're going to get residuals by default, and you can monitor those residuals for convergence. However, it's always a good idea to also monitor an important factor from your simulation to check how the model is solving and to make sure that your model is converging. So to do that, one of the most important values that we have is the heat transfer coefficient on the chips. So we're going to go ahead and create a new surface report. We're going to plot an area weighted average, and we're going to call this HTC chips. And we'll go ahead and keep that as area weighted average. We'll change our field variable to a wall flux. And from this drop-down menu, we'll do the surface heat transfer coefficient. And then we're going to select our fluid walls, which is those top surfaces of the chip where we're going to have all of our thermal transfer from. We can create a report file if we want to export this monitor explicitly, but in this case, we just want a report plot. So we'll uncheck report file. Go ahead and click OK. And we can close out of this window. So the final thing we want to do is we need to set the operating density for natural convection as part of the calculation. And the best way to do this is we're actually going to start by initializing the simulation. So we'll go ahead and initialize using the hybrid initialization method. And what this will do is this will calculate a very rough approximation of what our simulation is and use that as an initial condition for our calculation. This also allows us to come up to the results tab. We can go to surface integrals. We can look at area weighted average. We'll change our field variable to density. And then we'll plot the density at our pressure inlet. And we'll go ahead and click compute. And so now we see we have this value here. We're going to go ahead and copy that value. And where we're going to put that value, if we come back up here to cell zone conditions and double click, we actually have this operating conditions tab at the bottom here. So in this tab, we can actually set an operating pressure as well as set our gravity here. And the big one that we want to change is the variable density parameter. So we're going to check on the variable density parameter, and we're going to paste that value that we calculated from our model. And for natural convection, what we want to set this density to is whatever the density of our free stream or ambient condition is. So in this case, we have air coming in at 25 degrees Celsius. That will correspond to a density of air of about 1.184 kilogram per meter cubed. And we want to use that in our calculation to calculate the buoyant forces. And you want to make sure you define this with pretty high accuracy. And that's why we didn't calculate it by hand, but we actually initialized the simulation, saw what the model was using as the inlet density, and then applied that to the variable density parameter. So we can go ahead and click OK. And with that done, we can come over to the Run Calculation tab, and we'll make a few changes here. So for our pseudo time step settings, in this case, I actually know that this simulation is going to be stable at about 1.5 seconds for the fluid timescale and 1,000 for the solid timescale. If you're unsure of how to set these, you can just leave them on automatic, and it usually does a fairly good job. We'll then go ahead and increase our number of iterations to 500, and we should be ready to solve. So we'll go ahead and click calculate and start solving the model. So as our simulation starts calculating here, we're going to get two windows. We're going to get this report plot that we set in the monitor tab for the heat transfer coefficient on the chips, and we're also going to get our default scaled residuals here. So what we want to look at as we start solving is we want to look at the residuals and make sure they keep decreasing. For natural convection models, this can take a lot of time and a lot of iterations, so don't be too discouraged if it stays pretty high for a long amount of time before it starts going down. More importantly, what we really want to look at is our monitor point. And what we're looking at here is we want to make sure that this value stabilizes to a consistent point and isn't changing over iterations. And when both this converges as well as our scaled residuals converge, we can be pretty confident that our model is well resolved and has minimal convergence error.
A few moments later.
So if we take a look at our residuals here, we can see that all of our residuals, our X, Y, Z velocity, our continuity, as well as our energy is converging pretty well. We can also look at our heat transfer coefficient on our chip, and we can see that it's starting to flatten out pretty good. So the simulation interrupted itself at about 125 iterations. And this is because by default, our residual convergence criteria is set to 1e-3 for the XYZ in continuity and 1e-6 for the energy. Once that convergence criteria is hit and those residuals fall below those levels, Fluent will stop the simulation. In this case, since our residuals are still converging, as well as our heat transfer coefficient is still flattening out, we're going to want to simulate this for a little bit longer to increase the accuracy of our simulation. And to do that, we can come up to the results tab. We can go to residuals and we can set our convergence criteria. So in this case, what we're really looking for is the heat transfer coefficient or the calculation of the energy. And we want to make sure that's being accurately captured. So we'll go ahead and reduce that convergence criteria to 1e negative 8 and let the simulation continue solving to get a more accurate answer. So we'll go ahead and click OK, and we can continue calculating from this point. So in just over about 100 more iterations, we've converged and hit that second criteria point of 1e negative 8 for the energy term. And we can take a look at our residuals, and we always want to see these residuals going down in a smooth manner. So this convergence is actually looking really good. And we can also, again, check our heat transfer coefficient or our monitor point and see that that is very flat and fairly well converged. So we can be pretty confident now that our simulation is converged and our iteration error is going to be relatively low. So the first thing we want to do is we now want to take a look and make sure our model is doing what we want to do from a qualitative sense. So to do that, we'll plot some contour plots. So the first thing we're going to do is we're going to come down to the results tab here. We'll go to surfaces, we'll right click and add a new plane. And we're going to start by adding a plane in the XY plane, and we'll put it out about 3 millimeters in the Z direction. So this will slice right through our chips going up vertically. And we'll call this XY plane. With that plane created, we can expand our graphics window. We can go to contours and right click and add a new contour. We'll call this velocity contour. We'll make a contour of velocity and keep it as velocity magnitude. And then we'll select the plane that we just created. And we can go ahead and save and display. So what we can see here is we can see that as the heat is flowing over the chips, it's increasing in temperature, which means the density is decreasing, and that is creating a natural convection or a natural flow as the air moves over those chips. So we can see this looks exactly like we expect. We get these two streams of fluid moving up from each of our chip stacks. The other thing we can check here is we can plot a new contour and look at our heat transfer coefficient on the chips. So we'll go ahead and create a new contour. We'll call this HTC chips. We'll plot a contour of wall fluxes, and then we'll select the surface heat transfer coefficient. And we're just going to go ahead and plot this on the fluid walls or the walls of our chip, which are in contact with the fluid. And we'll go ahead and save and display. And what we can see here is that we have a slightly higher value of heat transfer on the bottom of the chip where the air is the coldest, and it gradually decreases as we move into the chip, which is pretty expected. So now that we know qualitatively that our simulation is acting in the way that we expect, we can start looking at some quantitative numbers and compare those to our calculations. So to do that, we'll come up to the top here. We'll go to the results tab. We can go to surface integrals, and we'll look at the average heat transfer coefficient on these chips. So again, we'll select our field variable of wall fluxes. We'll change this to surface heat transfer coefficient, and we'll go ahead and select that fluid wall. If we compute that, we see that we're getting a value of 14.97 watts per meter squared Kelvin as the average heat transfer on all of our chips. That's a little bit higher than the value of 12.52 that we use in our calculation, but that makes sense since this simulation is tracking the fluid flow and not using an assumption about the heat transfer coefficient and not using a uniform heat transfer coefficient. It is expected that we're going to have a slightly higher value for heat transfer on those chips. So to answer the big question, which is what we wanted from this problem, is how much heat can these chips dissipate? And to do that, we can come back up to the results tab. We'll go to the fluxes window, and we can come to total heat transfer rate. We'll select all of our faces, and we'll go ahead and click compute. And what this is going to show us here is the total heat in watts that each surface is dissipating. And what we can see is that our fluid walls, which again is the tops of the chips, is dissipating about 0.941 watts from all four chips. And if we compare that to the calculated value of our hand calculation, which was 0.939 watts, we can see that we're getting a very accurate answer compared to our analytical solution. So this total heat transfer rate is also going to take into account both the convective heat transfer as well as the radiation heat transfer. If we want to split out those two, we can come to the radiation heat transfer tab. Again, go ahead and compute and look at that same surface. And we can see that we're dissipating 0.257 watts of radiation from each of our chips, or from all of the chips together. And again, if we compare that to our hand calculation of 0.273, we're also getting a very accurate representation of the radiative heat loss from the system. So overall, when we combine both radiation and natural convection, we can get very close to our analytical equation and prove that we have a very good simulation that is accurately capturing the problem and giving us an accurate result for the simulation that we're trying to set up. So the next thing we want to do is we want to look at the forced convection case, or problem B. And to do that, we run into one problem, and we're going to have to do a little bit of math before we set up our simulation. So the problem we have for part B of this problem is that they only give us a heat transfer coefficient of 250 watts per meter squared Kelvin, and they say it's forced convection, which means we have a flow through our enclosure that is cooling the chips. However, for our simulation, the heat transfer coefficient is calculated during the solving of the simulation, and therefore our only control is the boundary condition, or the inlet velocity, that we can set in our simulation. So what we want to do is we want to make an assumption of what our inlet velocity should be to achieve a heat transfer coefficient of 250 watts per meter squared Kelvin on the chips. We have these empirical equations that allow us to estimate the Nusselt number and in turn estimate the heat transfer coefficient on flat plates. In this case, we're going to use the Nusselt number of 0.664 times the Reynolds to the 1/2 power times the Prandtl to the 0.33 power. We also have this equation for the Nusselt number is equal to HL over K. And what we can do is we can actually set those equal to themselves by combining these two equations. And with a little bit of rearranging, we can actually solve for the velocity term, which comes out of our calculation of the Reynolds number. And everything else in this equation is going to be known. So our heat transfer value, H, is given to us as 250 watts. Our length, or our characteristic length, we know is going to be the side of the chip. Our K is our thermal conductivity of the air. Mu and rho are both the viscosity and density of the air. And the other term in the calculation of the Prandtl number is going to be Cp, which is the specific heat of the air. So since we know all of those, we can actually solve for velocity. And if we plug in all of our numbers, we'll get a value of about 62.9 meters per second squared. So we're going to use this as our starting point in our simulation and see when we apply this boundary condition, how close we're going to get to this heat transfer coefficient, which we expect. Now that we're back in Workbench, we're actually going to reuse the geometry and the mesh as well from our previously simulated natural convection case. So we can come to our Workbench system here and just go ahead and duplicate that system. So with the system duplicated, we can go ahead and jump right to the setup window, double click. We'll leave double precision and our solver processes to 4 and go ahead and open the Fluent window. So now that we're in our new Fluent window, we know a few things about this problem. Since we have an inlet velocity of 62.7 meters per second squared, and the anticipated heat transfer coefficient is going to be 250 watts, which is much, much higher than the natural convection case, we know that natural convection isn't really going to play a role in this model. And because of that, we can make a few changes to the model and remove what we added in for natural convection, since we're only looking at forced convection. So what we're going to do is we're going to turn off gravity, since it's no longer going to be important. We can come to our materials tab and we can look at our air material again. And we can change this from incompressible ideal gas back to just a constant density. And we'll go ahead and change and create. We'll come back up here to the models tab, and based on our inlet velocity and the size of our duct, we're actually going to change from a laminar model to a turbulence model. So in this case, we're going to use the realizable K epsilon model. And since our mesh quality isn't really high enough to capture the full boundary layer, we're going to use a wall function to calculate the boundary layer. And the one that we're going to use is the enhanced wall treatment. The enhanced wall treatment is pretty good at calculating the boundary layer on non-ideal meshes and can work across either both coarse and very fine meshes. So in this case, it's going to be good for us. The next thing we're going to do is we're going to go to our radiation model, and we're going to have to recalculate our view factors for this case. So we'll go ahead and click compute and write, click OK. And we're going to go ahead and recalculate those view factors. And the next thing we're going to do is we'll come down here to our boundary conditions, and we're going to change our inlet from this pressure inlet condition, and we'll right click and go to type, and we're going to change that to a velocity inlet. So for the velocity, we're going to set that to our calculated value of 62.9, and we'll see how close we can get with this calculated value. Next thing in the thermal tab, we'll want to make sure that our inlet temperature is the 25 degrees Celsius that we were using for the previous model. And we can also just double check that our radiation is still set correctly. So boundary temperature and an emissivity value of 1, which is good. So we'll go ahead and click apply. The next thing we can change, since we're no longer doing natural convection, is we can come to methods and we can change our pressure discretization from presto back to second order. We'll leave our pressure velocity on coupling for this case, and we'll leave everything else as default. We're still going to use the pseudo time step method, which can help us solve this problem and get a little bit better convergence. We'll leave our under relaxation factors all the same as well. And we can go ahead and initialize using the hybrid initialization method. So once we're initialized, we'll come over to the run calculation tab. And the one change we're going to make here is we're going to move from user specified timescales for the pseudo time stepping method and go back to automatic, which will give us a little bit better convergence for this case. We can also come back to our results tab and we'll change our residuals here. And we're just going to make sure that the energy residual is set back to 1e-6. And we'll let the simulation simulate to these first convergence criterias, where we'll see how well the simulation is going, and then we can change them as required. So once that's set, we should be good to go, and we can go ahead and click calculate. So now that we've hit our first convergence criteria, we can take a look at our simulation and see how it's going. So looking at our residuals here, we're getting pretty good convergence. We do have a little bit of a hump in the middle here, but we are getting good convergence. Our energy is at about 1e-8, and everything else is being smooth and converging a little bit slow. If we look at our heat transfer coefficient, we can also see that that's stabilizing pretty well. So I'm just going to let this run for about another 150 iterations just to make sure that we don't have any iteration error, and then we'll take a look at the results. So after about another 150 iterations, we can see that our residuals have kind of stabilized and flattened out, and we're still getting pretty good convergence. And if we check our heat transfer coefficient, we can see that that is well and truly stabilized and converged. So I feel pretty confident about stopping the simulation here, and we can take a look at our results and see how close we got. So again, the first thing we'll look at is our qualitative values. So we can go ahead and plot a new contour, and we'll plot that velocity contour. And so in this case, we can see that we are getting our expected behavior where we have the velocity coming in from the bottom. It's kind of bumping up and accelerating up over the chips and splitting around the chips as it interfaces with the front wall of the front two chips. And if we plot another contour here of our heat transfer coefficient, we can also see that we have a little bit of a variable heat transfer coefficient. So on the edges of the chip that are getting a lot of flow, we have a pretty high heat transfer coefficient. And then kind of in the middle, we have a little bit of a different heat transfer coefficient, as well as these top chips are getting a bit of a different heat transfer coefficient than the bottom ones. So we'll create one more plane here, and we'll slice through the chip. So we'll create a plane. We'll call it the YZ plane. And we can go ahead and drag in the graphics window to slice through these two left chips. Go ahead and create that. And we'll plot another contour, and we'll call this the through chip velocity. And so what we can see going on here is that as the velocity comes in through the bottom, it's hitting the edge of that first chip and kind of deflecting up over the second chip. And it's going to give us a little bit of variability in that heat transfer coefficient because of the actual flow characteristics of our problem. And again, this is something that our back of the envelope calculation can't really take into account, where we're just using a uniform heat transfer coefficient, is it's not going to capture all these flow behaviors that may be affecting our simulation or our physical model if we're trying to validate to some experimental results. So again, we're going to check our quantitative values now and see how close we got to our back of the envelope calculation. And the first thing we'll look at is our area weighted heat transfer coefficient on all of our chips. So again, plotting the wall flux, looking at heat transfer coefficient. We'll look on those fluid walls. And you can see we're very, very close to our analytical equation, which gave us a heat transfer coefficient of about 250 watts on all the chips. We're getting about 252.56, which is very, very good, less than 2% error. And that also means that our calculation of the inlet velocity was pretty close to what we needed to get an accurate model. Finally, we'll get our final parameter for the total heat flux from the chips. So we'll plot on all the surfaces. And we can see that we're getting a heat flux out of the chips of about 15.86 watts. So when we compare that to our analytical model of about 14.37, we are still pretty close, but we are getting a little bit more heat transfer out of our model than the analytical model that we did. And that's pretty much expected because, again, our analytical model is just using a consistent heat transfer rate. It was uniform across all the chips. In this case, since we're actually looking at the flow, we're going to get all these weird flow behaviors where the flow is separating over the first chip and recirculating on the second. And all of that complexity is going to affect our heat transfer values. If we look at our radiation heat transfer, we can see that we're at about 0.261, which again is right in line with our previous simulation and right in line with our hand calculation. So that's still looking good. So overall, you can see if you have a problem that is relatively simple and can be solved with analytical equations, you can solve those in minutes by hand and get pretty accurate answers. But in this case, if you have a very complex flow field or complex geometry and those calculations aren't going to give you accurate answers, that's where simulation really comes to shine. And we can also see from this test case that simulation can give us very accurate answers and very usable answers for any engineering problem that we may run into. So with that, I'd like to say thanks for watching. And if you'd like to support the channel, you can hit the super thanks button below and buy me a coffee and help me with my PhD. And if you have any questions about this model or any model that you're working on right now, feel free to leave those in the description and I'll try to answer the question as best I can. Thank you.